So isn't it clever of me to come to Poland and name my talk after a Polish proverb, right? Not my circus, not my monkeys. I still think I love it. I mean, like, I love this saying. It's a great way, brilliant way to identify where to spend our energy and why we're spending it there. Letting go of the things that we're not responsible for. And I picture chaos monkeys running amok as the circus tent falls down. But I'm pretty sure that whoever coined this phrase was speaking metaphorically. I don't think he or she was actually talking about monkeys. I think they were sitting around the playground watching their children or watching other people's children play. And you know, when other people's kids start getting in trouble and you want to do something, and then you say, not my monkeys. And then you wonder where your monkeys went. So I'm Rob Martin. I'm VP Engineering for a startup in Utah. We do some machine learning stuff just like everyone else. Quality correctness is pretty important for us. We've got a nearly entirely pure functional stack. I have interns and juniors who... I have interns and I have juniors who have never worked in an object-oriented language. I have seniors who come to work for us even though I have to pay them peanuts because they get to come to work with us. And that's really cool. I like that. My talk is kind of a kitchen sink manifesto, so I'm just going to start in the middle. I wonder, how do we tell what a senior is? And I think that, you know, you can't, if it's something you have to count, you can't use it. It's not the number of hours, the number of years, number of languages, number of projects. I really think that it's about someone who delivers simple, demonstrably correct code, and with that, delivers value to the user. So let's go 10 times further, or something like that. How do you tell what a 10x developer is? You know, this was really popular a couple of years ago. There were a bunch of talks saying, you know, they don't exist, whatever. So I want to suggest that they do exist, and that maybe we've got a little bit of it wrong. You know, it's originally based on some research in 1968 by Sackman, Erickson, and Grant. Fred Brooks put it in the Mythical Man Month in 1975. We typically refer to it as like 10 times better than the average developer. That's not what the research said, or the research that's, you know, like demonstrated that the original research, which was flawed, still basically came to the right conclusion. What they said is that the actual studies demonstrate that there's an order of magnitude difference between our most productive and our least productive developers. But what metrics do you use for that? And what use are they? I mean, if you're working on some large government contract, I can imagine that, you know, COCOMO, the constructive cost modeling, is useful. Probably is, or function points, or the cyclomatic complexity of the project as a whole, rather than measuring it after we're done with it, measuring it before. These all could be useful, but for me in smaller, mid-sized companies and startups, what I want is value. So I focus on a 10x developer being somebody who can deliver an order of magnitude more value. But what is value? We're developers. It's a pragmatic art. It's not it's not an aesthetic art, right? We make tools. We make the tools that other people use to build rich lives. We aren't the sculptors. We are Michelangelo's blacksmiths. That's what we do. The degree to which our tools meet their needs in building the lives that they want is like how I define value. That's how I want to look at value. And as programmers, we deliver this value depending on where we are in the product cycle, based on the kind of judgment that we bring to our projects. More importantly, what kind of judgment we brought to our projects along the way. So let's say that we do have a 10x developer, and to become a 10x developer, we need to deliver 10 times as much value. Value comes from judgment. So how much judgment does it take to deliver 10 times as much value? This is just a thought experiment. I'm sure like lots of people can demonstrate this wrong from experience. Some of us will demonstrate it right from experience. But let's say developer A consistently makes decisions on a project that deliver 25% more value per unit of effort. Developer B is an average developer and gets 1.0 times as much value per decision. And developer C is one of our least productive developers and gets 25% less value per decision along the way. And I'm going to accept it as a given that these decisions affect the future decisions. So if we make a bad decision or a good decision up front, it compounds. So if we have 10 compounding decisions, then the difference between developer A and developer B is an order of magnitude, 9.31. Scarily, the difference between developer B and developer C is also an order of magnitude, 0.056. So thought experiment, 2 orders of magnitude difference. And of course, you know, that requires looking at developer C, who's our least productive. And we all know that our least productive developers can deliver negative value. I work on, you know, not just creating 10x developers, but creating teams of 10x developers by improving their judgment. There's a bunch of things I do for that. I guess first off, I'll tell you about some of my goals over the past few years. Building teams of functional programmers that productively include juniors. That's really important to me, the juniors. Migrating teams of imperative programmers and their legacy code into functional programming. Teaching functional programming to new developers especially. Been learning how to do that now for about 2.5 years. And now, like, my biggest goal is I'd really like to learn how to take somebody from an intern to a senior, measured by judgment and the value they deliver in 4 years. I understand in Poland that's considered slow. In the US, yeah, it's a little on the fast side. I think that value is great, but we offset it with anti-values, and I want to get rid of these. This is part of where our judgment comes in, because it's almost as if in the product life cycle, the decisions we make now are the ones that we have to, the ones that create the problems that we have to solve in the next stage. And I think you can actually see this in a lot of different places, right? The seed of our discontent, or we cause our own difficulties. Monolithic code is rigid, tightly coupled from one front end to one back end. It's often fragile. It tends towards complexity. Our code is often, especially early in the life cycle, especially with startups, our code is often untested. It's harder to work with because of that, and it tends to ship with more bugs. Our agile methodologies prioritize features, and they do it in an iterative and explorative way, right? This is wonderful, this is perfect, this is our best practices, and it ships technical debt every single time. Because we don't know what we're doing until we have a customer say, yeah, that's it, perfect, I love it. And then product says, good, let's move on to the next feature, because that's a higher priority than fixing the technical debt that we just shipped. And resolving that technical debt, yeah, has a lower priority, so we don't do it, not nearly often enough. You talk to agile leaders about this, and they'll say, well, yeah, this is a discipline we have to follow. We have to set time aside for it. Somehow, we don't have all that many agile leaders on our product teams. Maybe we should. So if we go to the typical route, excuse me, we deliver quickly, we prove our value, and we succeed. Yay. We get widespread adoption, and our servers start to fall over, and we upset, frustrate our users, and we start to refactor our code, rewrite our code, often in more functional programming languages. You know, we may have started in Django or Ruby on Rails. If we work harder at managing our anti-values up front, we deliver quickly, we prove value, and we succeed, yay. We get widespread adoption, and we don't fall over nearly as often. I am absolutely convinced that I can deliver startup code using Elixir and Elm that will scale at least 10 times further than comparable code that startups have been using for the past 12 years. So we don't have to rewrite, we don't have to refactor our code significantly. And there's this thing that we'll get into in a little while. The architecture that we end up with allows us to innovate around our core competencies. We can not have just one front end and one back end. We have a back end that's decoupled from the front end, which means that we can reuse that back end in new and interesting ways that people like to pay us for. I found my monkeys. Their names are simple and demonstrably correct. And you might have heard of them because I talk about them all the time. Okay, so simple. Let's describe simple by looking at the other side of the coin, which is complexity. Sandy Metz, she's big in the Ruby community. Some of you may have heard of her. She has rules for developers, and one of her rules for developers is that no method may be more than 5 lines. She includes the method declaration in that. My interns and juniors have a role that between the do and the end in their Elixir code, they're allowed to have 5 lines of code. That's about as decomposed. I mean, if you can't get it down to there, I wonder whether you're trying to do too much with it. The interrelationships and our dependencies, the degree to which one piece of software is dependent on another. Complexity is the enemy of reliability. That's like a famous quote, I forget. The central enemy of reliability is complexity. That's Dan Geer. Simplicity is a prerequisite for reliability, Dijkstra. The price of reliability is the pursuit of utmost simplicity. That's Tony Hoare. Complexity is a part of our code that's not beautiful. I like this. It's like beauty is the ultimate defense against complexity. And sorry, I don't know how to say his last name, Dan Galertner. Anybody want to shake their head vigorously and say I got it all wrong? Okay. And then I want to say that complexity is also code. Just, code. Brooks in No Silver Bullet says you got essential complexity and you got accidental complexity. But when it comes down to it, he's still saying all code is complexity. And if we could solve our problems as effectively without writing code, we would probably do that. And it would probably be simpler than the way we do it now. So complexity is bad. We probably know this. It's difficult to reason about, either formally or informally. It's difficult to test. It's difficult to tell whether or not we're testing the right stuff. It's difficult to trust complex code. If we can't reason about it, we can't prove it, why should we trust it? Tony Hoare again, and I met him in London, sat down with him for a little while. It's really amazing to have these opportunities that we do. And me coming from the States, to meet so many of my heroes here. John is in the front row, and I have an essay that is called Why Be Functional? And of course, the first thing I do is quote why functional programming matters, right? So Tony Hoare says, I conclude there are 2 ways of constructing a software design. One of them is to make it so simple that there are obviously no deficiencies, and the other way is to make it so complicated that there are no obvious deficiencies. I contend that the first one is the harder. I think all of these quotes that are 20 and 40 years old are still relevant. I don't know if you agree, but I think they're relevant. So what's simplicity? It's pretty simple to say it's just code that's not complicated, right? And that's a pretty good answer. I have a test called the simplicity test. I use it for evaluating code that I wrote or my team wrote. I use it for looking at library code and deciding whether or not I want to use it, or framework code. I use it for looking at a programming language. Or even like in talks I give on why be functional, looking at entire programming paradigms, like object-oriented versus functional. You know, is object-oriented programming easy to reason about? Is functional programming easy to reason about? Can I reason about this code? Can I demonstrate that the code is correct? Can I trust the code, right? And if I can answer yes to all three of these questions, my code won't just be simple, it'll be less fragile, it'll be more maintainable, it'll be less expensive to maintain. If it's simple, it's less likely to rot. I think that's why functional code doesn't rot the way that object-oriented code does. And what I like and what I'm excited to get into here is the impact that the same approach can have on architecture, the designs that we're following. But first, we'll get to architecture. Anyway, so we have code reviews. On my teams, our code reviews are really kind of based on the simplicity test as well. We look at the tests first, see whether or not they cover the business objective that we had for the feature or the bug that we were working on, right? Then we look at the code under the test and see whether or not it's easy to reason about. And then we look at that code in the context of the big picture and decide whether or not we can trust it with the system that we've got. So the simplicity test is useful for evaluating code, but it's definitely useful for evaluating the tools we use to create code. So for instance, for functional programming, I can ask, can I reason about this code? The answer, I think, is yes. We've got referential transparency that promises us that we can trust the result of our functions based on the arguments that are right in front of us, right? We've got composition that gives us different levels of abstraction. We can look at our code. We've got immutable state, so we always know the value of things. When we transform state, we get a new state back. Our side effects are isolated. They're obviously supported in most functional programming languages, but it's much, much easier to isolate them. Can we demonstrate that functional code is correct? Yes, of course we can. It makes unit testing very easy, integration testing easier, and proving correctness possible. I mean, like most imperative code is very difficult to prove that it's correct. Again, you know, referential transparency, pure functions, composition, side effects. The fact that functional programming is based on math makes a huge difference in like testing it, right? Dijkstra again. Programming is one of the most difficult branches of applied mathematics. The poorer mathematicians had better remain pure mathematicians. Okay, functional programming, can I test this code? If I can reason about it, if I can demonstrate that it's correct, I'm much more likely to test it. So I want simple and demonstrably correct code. I'm going to base it on pure functions. We already know a lot about pure functions. We just talked about them in evaluating like functional programming, right? We've got referential transparency. This is how I describe these concepts to new developers. So some of you will want to throw things at me, and some of you might say, oh, I wish I knew that earlier, right? Referential transparency returns the same value regardless of the arguments that we give it, right? Which another way of saying that is any given function can be replaced by the result of that function call in place without changing the meaning of the program. And another way of saying that is that nothing about the state of a program or the world can impact the result of a function call, a pure function call. We have immutability, right? I think it's absolutely ridiculous. It makes me want to grab that we have invariable variables. It's always fun to explain to juniors. So I try not to use variables. I try to use words like state, but then I explain to them that maybe it's easiest if you don't think about them as variables at all. Maybe we should think about them as functions. If we have referential transparency on our functions, then for any given argument, we're going to get the same value. If a variable is a function call that doesn't take any arguments, it's always going to give us the same value. We have function composition, so the output of one function can serve as the input to another. Higher level functions can be composed of lower level functions. We can move up and down through levels of abstraction. We have laziness, distribution. I'm worried about running out of time, so I'm gonna, we're functional programmers, right? Does this make sense? Okay. I see one hand go up. Is that a yes? Good, it made sense right there. So, okay. So, the lowest hanging fruit that we get from pure functions and functional programming, we can apply, well, to most programming languages, right? And many of us don't get to work in the programming languages that we want to. And one of my goals is to help people move from imperative and object-oriented programming languages to functional programming languages. So, I want to apply the lowest hanging fruit from functional programming to the work that they're doing. And it gives them an opportunity to become comfortable with the concepts in the language that they're comfortable with to begin with. And I'm going to start by saying, like the first rule is to isolate side effects from your logic. Simon Peyton-Jones, in the end, all programs must manipulate state. A program that has no side effects whatsoever is a kind of black box. All you can tell is that the box gets hotter. He is a venerable and wise person, but heat is a side effect as far as I'm concerned. So I disagree with him. Side effects, examples, you probably know these. It's, telling the time. Telling the time is a side effect. Getting API requests, reading from a database, writing to a database, replying to a client on an API, rendering something on the screen, adjusting the airlines on that intercontinental ballistic missile that you programmed. These are all side effects. Side effects are kind of like, the opposite of referential transparency, right? A pure function is going to give you the same result for the same request, but a side effect is probably going to give you a different result, but not definitely. Makes it interesting to reason about, right? So the plan for functional first programming is very simple. First, code everything you can without side effects. Write all of your business logic in pure functions. And then code your side effects, right? Preferably, put them in 2 different files, if I'm using Sinatra or Flask or Ruby on Rails or Django or whatever, I'm going to use as little of it as possible. I want everything I can to have no side effects, so I'm not going to be accessing the object relational mapper and hitting the database in the middle of my business logic, right? So I'm going to use the router. My controller is going to call my class full of pure functions. So in Elixir and Phoenix, I always just run mix phoenix.new, name of the app, no HTML, no brunch, no ecto, and no, there's one more. Nope, that's it. No HTML, no brunch, no ecto. So then, like my Phoenix installs run, let me see, boilerplate code, 125 lines, and my code, maybe another 40. So when we move our business logic in any programming language into pure, or as pure as we can get, functions, try to remember, for instance, in Python that you can't work on arrays without mutating them. You have to copy them first. So, it's not always easy to get pure functions. But we get some advantages. One of them is that we can work in the pure language, right? We don't need much by way of dependencies. There might be some libraries, for instance, for doing date math or whatever that we'll want to use, but we're not talking about big, heavy libraries that do a lot of I/O. We don't need those at all. Our code base is smaller. I think that as soon as you get rid of those dependencies and you're only dealing with pure functions, our code is a whole lot easier to reason about. It's certainly easier to test. Unit tests or breeze, and they run like instantaneously. Our functions are stateless. They're easy to scale horizontally. It gets us in a good place for architecture. And when we isolate the side effects, one of the really cool things is almost all of our side effects is I/O, right? And we don't write our own I/O libraries, not usually. I mean, if you write your own I/O libraries, that's cool, because there's some fun programming in there. But most of us don't need to do that. So when we're working on our I/O layer, on our side effects layer, we don't need to do any side effect, or we don't need to do any unit testing, because the libraries come with unit tests. All we're going to do is integration tests. And our side effects layer is as thin as possible. It's just side effects, so it gives us the opportunity to change it out, We're doing the least amount of work necessary to say, I want this instead of that, or I want this in addition to that. So maybe we start on HTTPS and we want to add WebSockets or HTTP2 or a message bus interface. Super, super easy. And with functional first programming, again, developers working in object-oriented programming languages pick up a lot of functional concepts. So working on a new project in a functional programming language is an ideal situation. Very, very few of us are lucky enough to have that. My last job had a legacy code base of 3 million lines of Java 6 with JBoss. It's a monolithic application. We were carving it up into microservices, but of course, we were still stuck with monolith. Whatever was still being supported by that code, we needed the whole of the code. And we couldn't break even the stuff that we weren't using in most cases, right? The longest class I saw in that code was 15,000 lines. The longest method I saw in that code was 5,000 lines. There were these two women who sat behind me. They refactored the 5,000 line method. It took them a month, which actually I think is pretty good performance. They removed like 3,600 lines of code in a month. And they were so good at pairing that I wanted to put them on a stage and make everybody watch them for at least an hour a day. Imagine refactoring 5,000 lines in one method and doing it with another person and enjoying. It's good. So I reported to a VP of engineering, and I ran an internship program. And my VP engineering, Scott, he said, "Hey, Rob, why don't you do a refactoring internship?" Okay, I laughed at him. I told him that it was the worst possible code for interns to learn from, that it's the worst possible code for brand new developers to work on, that the practices in there were horrifying, and that the interns are gonna, they're gonna hate the code, they're gonna hate the work, they're gonna hate their job, they're gonna hate getting up in the morning, they're gonna hate themselves, more importantly, they're gonna hate me, and if they're lucky, they're gonna become hairdressers rather than computer programmers. And I only say that not because I work with women who are in my internship programs. My buddy Joe and I owned a business together for a few years, like 15 years ago, and at that time, the field that had the highest job satisfaction was hairdressers. So we used to always joke, on bad days that it was time to go become hairdressers, as if we could learn that, quickly or something. Just like computer programming, right? Not something we learn quickly. So I laughed, Scott laughed, and then he said, "Do it anyway." That was fun. Fortunately, he quit before I had to do it. But in thinking about that, he's right. Juniors need to know how to refactor code. So it's good jobs. It's easier jobs for a junior to get. It's important work. So how could I turn that into something that actually moved them in a direction of writing simple, demonstrably correct code that relied on functional, the lowest hanging fruit from functional programming, right? So this was the basic process. You looking at it, you can see that I pretty much stole it from Michael Feathers, but I wasn't smart enough to ask him first, so I had to create it myself. Basically, it's you find the program area, you leave your side effects behind in the method, but you move your business logic in the problem area into its own function, right? And now you can just call that function. Except we're relying on class variables, we're relying on global variables, and we don't want to do that, so we're going to purify that function. We're going to take whatever it's relying on in its code. And we're usually only talking about like 6 or 8 lines of code that we're moving into its own function, right? So we're going to pass in anything that it's relying on. Once we've got that, then we haven't changed our business logic. At that point, we shouldn't have to worry about having broken anything. So now we write a failing test, a regression test for the issue that we're working on, right? And because we're there and we're writing tests, we're going to write some characterization tests as well that demonstrate how it actually works. Even if we don't understand why it works that way, we still want to make sure that it works the same way when we're done. Then we fix the code, pass the regression test, and go back and refactor to make it simpler, easier to reason about, easier to maintain, and still passing all of the tests. Okay, so I got this from Phil Wadler, and I thanked him for it, and he said, I never said that. It feels to me like some of our programming languages were built in a garage, and there's a reason for that. It's because they were built in a garage. Some of the garages were really, really big, but Java was still made in a some garage, right? These languages have a lot more abstractions, but they feel more concrete. You know, we've got many choices in how we're going to do it. And some languages have even, like, you know, sold themselves on there's more than one way to do it, right? We've got languages that are object-oriented and procedural. We've got languages that are functional and object-oriented. We've got frameworks and libraries that add new abstractions on top of the abstractions that the language is already providing us. And we've got, at the end, the illusion of choice with tons of hidden complexity loosely wrapped in abstractions that are, you know, held together kind of tenuously. Depending on the language, some much worse than others. I've used these languages, I've loved these languages. I've probably written more than 2 million lines of code in a lot of these languages. What I find is these languages require mastery in order to have judgment, good judgment. And if you don't have that mastery yet, it's difficult to have good judgment. If you don't have good judgment, it's difficult to deliver value. So I want to avoid these languages, right? Orwell, somebody gave a talk on Orwell, right? Freedom is slavery, choice, power. I think that it hurts us more than it helps us. But some languages feel like they're based on the laws of the universe, and that's because they're based on the laws of the universe. It's not a bunch of mismatched or abstractions. It's a few solid abstractions that go a lot further because they're based on math, logic, philosophy. We start with Lambda calculus for most of them, right? A few functional programming languages are primarily based on combinatorial logic. And we tend to add in type theory and set theory and category theory. And, you know, and you can look at this family of languages and you can trace, you know, like which abstractions they're based on and get a lot further with them. We all know this, I hope, because I hope most of us have the pleasure of working with these languages. Compared to the languages built in garages, these languages are very constrained. We don't have as much choice. We're not going to get in and, you know, deal with metal level things, at least not very easily. We don't have the power of a systems language. We don't have the power of Java or C++ or C or whatever, right? And that's what I want my teams to have. I want them to have a constrained language. I want them to be able to learn fewer abstractions. I'd like them to have fewer options. I want them to be able to focus on the problems that we're solving rather than understanding all of the options we have and how to solve them. Functional programming languages, again, this slide looks just like other slides. We've got characteristics of functional programming languages. These are the languages that very often feel like they are based on laws of the universe. And if we apply the simplicity test to them, I'm sure that you can probably do that in your head, but I'm going to rush forward. It is code that we can reason about. It's code that we can demonstrate that's correct, and it's code very often that we can test, or that we can trust. Again, with juniors, I like to have a simple way to explain immutability. And I tend to do that using identity, right? We use state in our program very often to represent things that are in the real world, right? In object-oriented languages, the properties of one object distinguish that object from other objects. Identity is the current state of an object. The current properties of that object are the identity of that object. The object-oriented abstraction gives us only one identity, the current snapshot of that object. We could, of course, maintain a journal, but we don't get this for free from object-oriented programming. In functional programming, state is immutable, right? So we transform state from one version to another version, which means we always have at least two versions of our state. We have the current and the next, or the previous and the current, however you want to look at it. By extension, that means we actually have every version of state, because we were the ones who chose what to throw away. And because of that, we can actually say that identity is basically an immutable collection of states over time. And it's very different between functional programming and object-oriented programming. Identity in functional programming is a collection of states over time. And we get this for free when we're using functional programming, and it's an extremely rich source of data for answering questions, even the ones that we don't actually know to ask yet. Once we have identity, we very often need persistence, right? So we have classes of databases. Relational databases tend to treat data like object-oriented programming treats identity, right? A query returns the current state of an entity. Updates are destructive in the standard abstraction. The database is mutating its data. The concepts behind relational databases are kind of brilliant, especially for the late 70s. And they don't match well with our current needs on this internet. And modeling complex data in relational databases is painful. I don't like that. And would like to avoid it when possible, because it's complexity. Then we have most NoSQL databases. There is no such thing as NoSQL. Everybody should remember that. This is sloppy convenience. It gets us eventual consistency, denormalization, and speed. At web scale, also a meaningless term, that we often have trouble doing with relational databases. They still treat our data like object-oriented programming treats identity, right? Updates are destructive, data is mutable, or at least it's presented to us that way. Like CouchDB doesn't actually mutate the data, right? And it keeps previous versions right up until you tell it to clean up. And then they're no longer available to you. And you can't query them. We're still getting that point-in-time snapshot of our state. And changes to our data are incremental and shared across multiple devices, so we need to manage conflict, which is, again, complexity. So then we have immutable databases, which do not destructively update our data. In fact, there are no updates with immutable databases. If we look at CRUD, we don't have CRUD, we just have CR, create, read. An update is just a create that says, hey, this is now that. We have the same benefits with immutable state in our programs and immutable databases in our persistence layer. We can reason about our data, changes to our data are idempotent. We've got an audit trail showing us when and where and why things changed. We can ask questions about our data over time. Our queries may even be pure functions against a bunch of events. There is a question about, CAP theorem. CAP theorem was influential, very influential in the creation of our NoSQL databases. And I don't know about you, but I first learned that CAP theorem was about databases. It's not, it's about distributed computing. And that's gotten me to ask, what's the difference between, what is a database? What's the difference between a database and something else? If I have row-oriented data, well, I probably have a database. If I have column-oriented data, I probably have a database. A key value store, an event store, a document store, we call these databases, right? But what about a web server? Why is a web server not a document store? What's a microservice? What's a search engine? And maybe the distinctions that we have between databases and services is not actually all that relevant. We still have to deal with all of the same things. Reactive manifesto, I'm guessing. Who's heard of it? Who's read it? Who uses it? Yay. Expectations from past architectures are inadequate of meeting the needs of today's internet. They say our previous expectations are too slow, too fat, and too unavailable. So they define a coherent system architecture that expects 100% uptime, millisecond range response times, cloud-based infrastructures, and petabytes of data. And maybe this is not what I need for my startup, but the ideas are wonderful and applicable. They're based on 4 characteristics: that our services are responsive, that we have rapid and consistent response times, that build confidence in the usability of our system. That response time also can be useful to indicate whether or not things are working properly. If we monitor our response time and we see, things go awry, well, that probably indicates that there's a problem. Reactive systems are resilient. They stay responsive even during a failure. The components are redundant, replicated, isolated, and we can delegate responsibility. If something goes down, we've got someone else who can pick it up. Our reactive systems are elastic, responsive even under varying workloads. Our designs avoid bottlenecks and contention points. We're constantly monitoring and automatically scaling. And reactive systems are event-driven, which gets us back to our immutable data, right? Asynchronous message passing. We're decoupling our systems and using that message passing to connect them back together. We avoid blocking communication, isolate our services, and we make the location of different services transparent. We don't care where things are at. Funny how much this sounds like Erlang. So creating reactive systems helps us design and build scalable, anti-fragile systems. It reduces the complexity of our systems. It aligns really nicely with those functional first concepts that we talked about, and it aligns really nicely with domain-driven design. What's domain-driven design? Again, I'm guessing that some people have been trained in, okay. So core concepts for domain-driven design are, well, domain-driven design, it's just an approach to developing software that's based on a collaboration between us and them, programmers and the people who actually work in the problem domains that we're solving. And our code actually ends up being organized around the way that they think and talk about the problem. So core concepts, a domain is an area of activity, a subject area or a sphere of knowledge. Model is how the people who work in the domain think about the problem. The ubiquitous language is the way that people who work in the domain talk about the problem. An entity is something that has identity, as we've already talked about, in the context of a domain. A domain event is something that happens that's important to the domain experts. It's within the context of the domain model, and it affects entities in that domain. Bounded context is a collection of related domains that share a model or models, share the language. They have many of the same entities, and they tend still to have their own domain events. If we do domain-driven design skillfully, we'll end up with code that's limited to a particular domain, well organized that way, depending on data structures describing entities on the models in that domain. And because we're using the same language as our business partners, we often end up with code and data structures that they can read and understand. And that's really interesting. Like, we write for our future selves, we write for the people who maintain our code. In domain-driven design, we're writing for the people who benefit from our code too. Compared to a context where we used to build these unified models of the business and monolithic applications, domain-driven design is dramatically simpler, faster and cheaper to maintain, and better at correctly solving business problems. The front end is its own domain. Reactive systems and domain-driven design lets us derive that. It may be the consumer side and the back end is the producer side, for instance, like in e-commerce or banking. It might be the other way around in data entry or Internet of Things or logistics or an ERP system, where the front end is the producer, the back end is the consumer. The purpose of the front end is strictly to manage the experience of the user. The domain logic on the front end can be performed on the front end. This is something that we don't necessarily always do because it's within a different domain. And the front end and various backends relate to each other as defined by the bounded context and their domain models and the entities and events within that context. The front end is a different domain. If the front end is a different domain, the back end is a different domain, or the back ends are different domains. The back end is responsible for maintaining the integrity of our data by applying our business logic. That's its job. We don't just have one of them, we create one for each domain. We group them within the bounded context. Based on functional first programming, we're going to isolate our side effects, keep all of our business logic together. I forget what I was going to say there. Oh, that's fun. This gives architecture, the same benefits that we get from functional programming, but at an application scale. A business logic is purely functional. It's referentially transparent. It's composable. With purely functional business logic and immutable data, it's easy to horizontally scale. Our business logic is really easy to test, and the tests run fast. Our side effects layer is only side effects. We cover those, again, with integration tests. That isolation makes it really easy to add multiple interfaces to our domain logic. So we get this bonus, then, that we can easily have multiple front ends and multiple back ends, right? If we're mashing up the back ends to form the front ends, then we can identify different domains for the front end. Maybe we have like one application that's more for staff and one that's more for management. Or we want a native mobile app or a public API. These are all things that are easier to do when we have that back end. So if we take this into a simple, overly simplified architecture with various client applications representing different domains, they generate domain events, right? Reactive programming. They generate these events within the bounded context, domain-driven design. The events are persisted to an event store, which is an immutable database. The event store is queried for events filtered by the domain or filtered by domain for the domain services. Domain services generate domain events within the bounded context and hand those back to the event store, which then, other domain services pick them up and update their models. Client applications also subscribe to events that pertain to them. And client applications and domain services can query other domain services to answer questions about the domain model that they're responsible for. From here, of course, this is like minimal. We could still use Rabbit or Kafka for distributing events. We can shard domain models. We can access services from other bounded contexts and cross-cutting services like messaging or authentication. We can move the whole thing to AWS with S3, API Manager, Lambdas, Dynamo, Kinesis, and EC2. This is how we do our event store. And because of the timing, I'm just going to say that it's based on domain-driven design. You can see we've got a realm, a domain, an entity, and an event type that we're storing the data for. The realm is really organized around authentication. Our domain services are organized, of course, by domain, subdivided by the model. Each service requires or receives its events that we map to a function that we use to transform our domain model. This is really useful. Sometimes we'll receive those functions and process them immediately. We'll update our domain model. That's typically what we're going to do when we need to ask questions about the domain model a lot more frequently than we update it. So if I'm building a shopping cart service, I want to know what's in a shopping cart about 50 times more frequently than I want to change it. But if I'm running a shopping cart service and I want to know, hey, which products got left in shopping carts and then taken out right before they checked out, well, that's not a question I'm going to ask very frequently, so I might do that one on demand. Projections and reductions are two different ways of looking at that domain model. I'm going to skip that, sorry. Distributed computing, all I'm going to say is it's not invented here. As much as possible in this architecture, we're pushing the hard problems of distributed computing off onto software that does distributed computing. We don't work in that domain. I don't work for a research institution. I don't have a research team or a budget. And these are well-studied problems that are peer-reviewed and demonstrated to be correct. In summary, then, using the lowest hanging fruits from functional programming, that functional first approach, using reactive programming and domain-driven design, we end up with a system that we can reason about. We've got event sources and command query responsibility segregation. That pattern is simple, it's well understood. We've got domain-based design that's well organized. Our domain models and our events are immutable. Our events map to pure functions, and our domain models are just state transformations. We can demonstrate that our system is correct. Our domain logic is purely functional, right? Referentially transparent, easy to test. Our domain services are isolated. Our system of record is immutable and has a full audit trail. Reactive system design gives us monitoring for operational errors and distributed computing portions that were based on the hard stuff we didn't build. People who are putting that effort into it are taking care of that. Can we trust our system? Yes. It's easy to reason about. We can demonstrate correctness before and during production. We deliver value quickly and frequently. We can trust even our less experienced developers to produce value in these systems. We can avoid the anti-values that we discussed. We leverage our functional programming concepts, which I think helps us trust it. and we get the benefits from reactive programming and domain-driven design. And I'm sure there's not time for questions. Thank you.